Hello, welcome back to Learn Physics. In today's topic, we are continuing with electrostatic potential and capacitance. So, electrostatic potential, we learned till electrostatic potential energy of a dipole. Right. So, some of the conditions also we need to learn. After that, we will start capacitance. Okay, so today first we are starting with our yesterday's homework question. That is, first one, two charges of magnitude 5 nanocoulomb and minus 2 nanocoulomb are placed at points 2 centimeter 00 and x centimeter 00 in a region of space where there is no other external field. If the electrostatic potential energy of the system is minus 0.5 microjoule, what is the value of x? This is a previous year question. So, two charges are there, 5 nanocoulomb and minus 2 nanocoulomb. Nanocoulomb means 10 to the power minus 9 coulomb. Okay, are placed at points 2 centimeter 00, that is in x-axis at distance 2 centimeter, and x centimeter 00, x-axis at a distance x in a region of space where there is no other external field. No other external fields are there. If the electrostatic potential energy of the system is minus 0.5 microjoule, electrostatic potential energy is given as minus 0.5 microjoule. Okay, what is the value of x? So, in first one and second one, no other external field. External field are not there. So, how we can find out? 1 by 4 pi epsilon 0 q1 q2 divided by r. Right. So, using that we can find out the formula and we can find out the potential energy. So, that total potential energy due to the first one and the second one. So, total should be equal to minus 0.5 microjoule. We should find out the value of x. Shall we start? So, two charges are 5 nanocoulomb and 2 nanocoulomb. This is minus 2 nanocoulomb, and so it is Q1 and this is Q2. Q1 is at distance 2, 0, 0. This is x 0, 0. The total potential energy of the system, it is given as, at a particular point it is minus 0.5 microjoule. So, what is the formula to find out the potential energy? V is equal to, or U, potential energy we can represent it as U. U equals 1 by 4 pi epsilon 0 Q1 Q2 divided by R. So, this R how we can find out? Okay, this Q1 is kept at a distance of 2 centimeter. Okay, this is Q1 place and this Q2 is kept at a distance of x centimeter. So, suppose I am keeping the Q2 over here which is at a distance x, Q2. Okay, so we need to find out the distance. What is this Q1, Q2 divided by R12? So, what is this R12? R12 is x minus 2. Right. So, we can write it as, see, minus 0.5 into microjoule means 10 to the power minus 6. That is equal to 1 by 4 pi epsilon 0. Q1 is 5 into 10 to the power minus 9 coulomb into Q2 is minus 2 into 10 to the power minus 9 coulomb divided by x minus 2. Okay, now we can solve this. X minus 2 will be equal to 9 into 5 into 2, negative and negative will get cancelled, divided by 0.5 into 10 to the power 9 into 10 to the power minus 9 into 10 to the power minus 9 divided by 10 to the power minus 6. So, 9 and plus 9 and minus 9 will get cancelled. See, this one 5 and 0.5 while cancelling we will get it as 10. So, here 180 into 10 to the power minus 9 plus 6. So, 0.18. Here we forgot to find give the centimeter to meter, right? So 10 to the power minus 2. So that 10 to the power minus 2 also here. That one plus 2. It will come as plus 2. So it is 1.8 we will get. 180 into 10 to the power minus 1. So 18 we will get. Now how we can find out the value of x? X is equal to 18 minus, so plus 2, so we will get it as 20. X minus 2 is 18, so we will be getting at 20 centimeter. Okay, so this is how we will be finding out the answer for this one. Clear? Next one is an electric dipole of length 4 cm when placed with its axis making an angle of 60 degree with a uniform electric field experiences a torque of 4√3 nanometer. Calculate the potential energy of the dipole if it has a charge plus or minus 8 nanocoulomb. So it's in the question it is given as an electric dipole of length 4 cm. That is distance between the charges is 4 cm when placed with its axis making an angle of 60 degree. So theta equals 60 degree with a uniform electric field experiences a torque. Torque 2 equals 4√3 Newton meter. Calculate the potential energy of the dipole. Potential energy we need to calculate if it has a charge of plus or minus 8 nanocoulomb. That means plus equal and opposite charges, right? So it is given like this. We need to find out the potential energy. So what is the formula to find out the potential energy of a dipole? Potential energy of the dipole, yesterday we learned it as P dot E minus P dot E. That is minus PE cos theta. Okay, so this potential energy only we need to find out. For that, tau is given, theta is given, 2a is given. Okay, how we can find out? We know that tau equals P cross E. P cross E means PE sin theta. Right. So here how we can find out this potential energy we need to find out. Here for finding out the potential energy we don't have PE. So we can find out PE from here. P into E will be equal to tau by sin theta. What is tau? Tau value is given as 4√3 divided by sin 60. Sin 60 we know that it is √3 by 2. So we will get it as 8. So P into E we got it as 8. No, so potential energy. Here also I will write down potential energy. Otherwise you may get confused. Potential energy. How we can find out the potential energy? Minus PE cos theta. Minus PE means minus PE cos theta. PE is 8. Cos theta is cos 60 1 by 2. Minus 8 into 1 by 2. The answer is minus 4 joule. Okay, clear? So this is how we will be finding out the potential. It's easy, right? So we need to remember all the formulas. That is very important. Clear? So next we are going to find out the electrostatics of conductors. Electrostatics of conductor. How we can find out the electrostatics of conductors? So what are the some important points relating to this conductor? Okay, so in electrostatic equilibrium, the electric field inside the conductor is 0. That is very important. See, the electrostatic equilibrium, electric field inside the conductor will be 0. So how it is possible? I am considering a conductor. Okay, in that conductor, inside the conductor I am considering. Okay, so this is A and this is B. Okay, then E is the electric field which is acting in this conductor. Okay, this is a conductor. So inside part of the conductor I had given a small portion AB like this. Okay, here electrons are moving from here to here, this side. So because of that movements, here it is negative charge, here it will be positive charge. Because of this movement of these electrons towards the A part, and hence positive charges are forming here, right? Because of that, an induced electric field will be developed inside it, which is in the opposite direction. I am representing this as EP. Okay, so it is moving in the opposite direction. Here external electric field is in this direction. So it will be in equilibrium. When in electrostatic equilibrium, what will happen? This E minus EP will be equal to net electric field, positive, and this is opposite direction, negative field. So E minus EP will be equal to 0 in electrostatic equilibrium. No further charges moving through that. Okay, therefore electric field inside the conductor will always be equal to 0. Clear? So electric field inside the conductor is equal to 0. That is the first point. Next one, second one, outside the surface or outside or on the surface, electric field is normal to surface of the conductor. We can write it as just outside. Not outside means not far away. Okay, just outside or on the surface of the conductor, electric field is normal. Normal means perpendicular to the surface. That is, once all the electrons are rearranged, after that electric field is 0. Right, so if electric field is 0, then on the surface, while we are considering the surface of the conductor, electric field is acting along the tangent. Right, so here how we can, this is the tangent. Suppose the electric field is like this, you think. Then along the tangent, what is the direction? E cos theta. Right, so this is the tangent. Tangent is E cos theta. If electric field is 0, then the tangential component will be E cos theta will be equal to 0. When E cos theta will be equal to 0? When theta equals 90 degree. Okay, that is how we are telling this electric field will always be perpendicular to this surface. Okay, in an electrostatic field, just outside or on the surface, the electric field is normal to the surface or perpendicular. So in direction means it will be depending on whether it is positive or negative. If it is positive means direction of electric field is outwards. If it is negative means direction of electric field will be inwards. Okay, all the positive charges direction will be outwards, and all the negative charges direction will be inwards. Direction of electric field is inwards in the negative charge. This and all we learned, the direction and all we learned in the first chapter itself, right? So here this is the second point. Now, so we got it as electric field inside the conductor is 0. Then we on the surface, electric field will be perpendicular to the surface. Okay, next, what will be the charge? Net charge inside the conductor will be equal to 0. Net, this is the third point. Net charge will be equal to 0. How we can prove that? See, we know that closed integral E dot ds is equal to Q by epsilon 0. Right, if E is equal to 0, what will happen? Q will be equal to 0. Since E is equal to 0, we can write it as Q will be equal to 0. Net charge inside the conductor also will be equal to 0. Okay. See, next is fourth one. We already told electric field just outside or on the surface of the conductor will be normal to the surface, we told. What will be the value of this conductor? See, I am considering a conductor. What value of this electric field? Okay, we are going to find out the value of that electric field. I am considering, so this is the surface. Okay, surface I am considering like this. Okay, here I am considering a cylinder, which is, see, if this is the conductor, I am considering a this is a electrostatic conductor which I am considering. In that I am considering a cylinder, and in this manner. Okay, half is inside, half is outside. Okay, so how we can find out the electric field over here? Inside that electric field will be equal to 0. Inside electric field will be equal to 0. But outside how much it will be? We know that closed integral E dot ds is equal to Q by epsilon 0. E into ds, closed integral ds will be equal to Q. We know how we can represent Q. Q is surface of the conductor only we are considering. So surface charge density, total charge on the conductor, that is surface charge density we should consider. What is surface charge density? Sigma will be equal to Q by A, area, surface charge. So here we are considering it as ds for a small charge. So I am considering it as integral ds, closed integral ds only I am considering, since it is the closed surface like this. What is the surface area? If it is a cylinder, according to that we can consider, or if it is a sphere, according to that we can consider. Closed integral delta s. Okay, so what is Q? Sigma into closed integral ds divided by epsilon 0. So ds will cancel, we will get it as sigma by epsilon 0. So E on the surface of a charged conductor will be equal to sigma by epsilon 0. Surface charge density divided by epsilon 0. Whether if sigma is greater than 0, E also will be greater than 0. That means sigma is positive. Sigma is positive once Q is greater than 0. That is Q is positive. Positive or negative, depending on that E can be outward or inwards. If sigma greater than 0 means Q is positive. If Q is positive, E will be outwards. Clear? Then if sigma is less than 0 means Q is inwards. Q will be acting inwards. Clear? So the next one is electrostatic shielding. Electrostatic shielding. What is meant by electrostatic shielding? See, it's a simple case. That means, see, inside a car, during lightning, if we are safe inside the car, the processes that explained with the help of this electrostatic shielding. So it's a conductor, car is a conductor, but if we are closing, see, everything is closed and we are there inside means, see, all the windows are closed and we are there inside means that electric field will be, we won't get the electric shock, because the electric field inside the conductor is equal to 0. Okay, for a conductor, inside the conductor, if I am considering a cavity, in that cavity electric field will be equal to 0. That is, electric field will be 0 inside the conductor. So that is called the electrostatic shielding. So electric field, but what about the potential at that case? We didn't study that one, right? So what is the potential in that electrostatic potential? Potential will be remaining constant over there. P will be constant. What is the reason? Because A is 0. So V minus V, this electrostatic potential will be equal to 0 over there. See, potential difference is 0. That is VA minus VB will be equal to 0. That means VA will be equal to VB. Potential remains constant over there, but electric field is 0 and surface charge density also will be 0. Clear? So these are the main points which we are studying today. So here, first one is electric field inside a conductor. In an electrostatic condition, electric field inside the conductor is 0. On the surface, while we are considering surface component will be acting, electric field will be acting perpendicular to the surface component. Right? It will be surface, perpendicular to the surface or normal to the surface. Okay. So the next one we learned is electric field. What will be the electric field on the surface? Will be equal to sigma by epsilon 0. And next one is electrostatic shielding. Inside the cavity of a conductor, electric field will be equal to 0. And then we learned about the potential, but the electric potential remains constant inside the cavity. Clear? So next one is next topic I can say how we can store these charges. Okay, see, we were studying about these charges and potential energy due to the charges, all those things we learned. Okay, now how we can store those charges? The ability of a conductor to store the charges, that is called a capacitance, electrical capacitance. Okay, electrical capacitance is the ability of a conductor to store the charges. How these charges can be stored? See, that and all we will be studying after this. See, like ability of a conductor to store the charges, that is electrical capacitance. That ability is called as capacitance. So, as capacitance, how we can measure the capacitance? See, a capacitance is represented by C. The charge stored in the capacitance, that ability, how much of charge is storing? Charge stored will be directly proportional to the potential. Okay, therefore we can write it as Q equals CV. This C is called electrical capacitance. Okay, so this C is called as electrical capacitance. Okay, so Q, then what is the unit of C? Next is unit of C. Unit of C is farad, represented by F. Okay, so it is not a meter is the SI unit of length, right? But there nanometer, picometer, so many units are there, right? Same way here also we will tell about microfarad. Microfarad is 10 to the power minus 6 farad, and picofarad also there, that is 10 to the power minus 12 farad. Okay, so this is about the capacitance. Understood? How? See, capacitance is Q equals CV. Capacitance is the ability of a conductor to store the capacity, to store the charges. Okay, now the apparatus used for storing these charges, that is called as capacitor. Capacitor is the apparatus used to store these charges. So how we can make a capacitor? Capacitor means charges should be stored, right? So here I am taking a conductor. It is positively charged conductor. Okay, it is positively charged, and A is a positively charged conductor. I am taking another charge, another uncharged conductor B over here. What will happen? Because of this positive charge, all the negative charges will be stored over here, right? And here at the other end, positive charges will be coming. So next what we will do here, this one already we learned in the first chapter, remembering, right? So all these were positive and this negative charges are there, and the opposite side what we will do, we will be earthing this conductor. Okay, so all the positive charges are going to the ground. Now here positive charges existing, here negative charges are existing. So this will be the storehouse of this charges. Okay, so large amount of charge can be stored over here, that is called a capacitor. So usually we will be connecting positive end over here, negative end over here, so it will be just storing the charges. Okay, so this is called as a capacitor, and for this the distance between this will be very small. Distance between these two conductors will be very small compared to the area. So here area will be very small compared to this, very large compared to the distance. Okay, distance is very small compared to the area. Area is big and the distance, that is very closely arranged, this will be. So if we are taking two parallel conductors like this, then we can say it is parallel plate capacitor. Parallel plate capacitor. If I am taking two parallel plates like this, I can consider it as a parallel plate capacitor. If I am considering spherical conductors like this, then it will be a spherical capacitor, or if I am taking a cylindrical conductor like this, we can consider it as cylindrical capacitor. Okay, clear? So this is just an introduction for this capacitor chapter, capacitance. So ability of the conductor to store the charges, that is called a capacitance, and this This is unit is farad. Formula also important. Formula how we can write, C equals Q by V. Okay, this formula also very important formula, C equals Q by V. Okay, clear? So one more thing, you should maintain a formula book, and while you are learning all these things, in between important points, see, I have some difficulty in this giving the notes as a printout form, because so many equations are there and vector symbols, that and all I am feeling it difficult to print. Okay, and now you know it is, everything is, shops also closed, I can't take the printouts from outside also. So while you are just, this is just I'm just helping you to read the textbook. So read the textbook in between, prepare your own notes. Otherwise, whatever I am telling this as teaching you, that time you can write down and keep, and important points which are in the theory part I will keep. But don't forget to write down and study the this one, what is the derivations. Derivations are very important, along with that formula and unit. If you know the formula, it's very easy to find out the units. Okay, here itself we know coulomb per volt, that is equal to farad. Okay, so that and also that formulas and all you should learn properly. So this much only I am taking it today. Okay, I hope it is useful for you, and if you like the channel, please don't forget to subscribe, like and share. Okay, thank you for watching. Bye.